All right, so section 9.7 is sort of the last of this initial whirlwind of random facts that prepare us to do calculus in 3 dimensions. And this one's going to be about something called quadratic surfaces. And we'll just say those are non-flat things. We learned how to write equations for lines, equations for planes. This is going to tell us about equations for things that are a little bit more curvy. And then the equation for a quadratic surface is going to follow this general form, which I don't think it's very necessary that you copy it down, but it's ax squared plus by squared plus cz squared. And then kind of it can have all these cross terms, dxy plus exz plus fyz plus efg x plus hy plus iz plus something that doesn't have any variables attached to it equal to 0. That's a whole mess. Really what's important to know is that they're called quadratic because they've got these square terms in them. These cross terms are sort of like squared terms. It's just instead of having 2 x's, you can have an x and a y, an x and a z, so on and so forth. And the different weights that we put in front of all these things, letters A through J, determine what the specific surface is. And so all we're going to do is kind of look at all these different equations and then build intuition for the different surfaces we'll see later in class. And I'm just going to tell you to look at page 736 for sketches of surfaces. If there's anyone who doesn't have the textbook when we cover this section in class, you can just come to me and take a picture of this page in the book. I'll bring it with me. It has a lot of really nice pictures of the different surfaces that I couldn't possibly recreate because it's hard to draw in 3D. But we'll just talk about kind of some basic surfaces for now. So a cone is going to be given by z squared is equal to x squared over some a squared plus y squared over b squared. And this a and b determine how steep the cone is. And it's always going to be kind of like a z, x, y. There's this kind of shape. All right. Kind of cone-ish, I guess. I don't know. Like I said, drawing is really not my strong suit here. The pictures in the book are better, but hopefully you can tell this is like an ice cream cone. The upside of it is the positive branch of when you go and you do square to get the z, and the bottom part is the negative branch. If this A and B are the exact same, you're going to get one of those cones that's kind of perfectly circular. And that type of shape in particular is going to come up a whole lot when we're integrating. So please remember that special type of cone. A sphere has equation, we learned x minus a squared plus y minus b squared plus z minus c squared equals 0, or sorry, equal r squared. And in particular, the sphere centered at the origin, a equals b equals c equals 0, is centered at origin. And spheres are just big circle things. We should have labeled this, I guess, x, y, and z. And just like the cone, the top part of the sphere is coming from when you solve for z and take the square root of everything and hold on to the positive branch. The bottom part of the sphere is the negative branch. Let's do hyperboloids, I guess. Actually, let's do paraboloids first. So a paraboloid is kind of like a parabola, but now in 3 dimensions instead of 2. And so it's going to have shape given by z equal to x squared over a squared plus y squared over b squared. And it's going to look like a slightly less sharp cone. So let's give it a clearly rounded bottom there. There we go. No. The more careful I try to be, the worse it is. Okay, so it's kind of like that, more rounded. Than a cone. And since the z doesn't have that squared term like cones and spheres do, there's no negative part. That's how you can distinguish a paraboloid from a cone or a sphere, or in particular, a hyperboloid. Boloid. Which when we have x squared over a plus y squared over b minus z squared over c equal to, it can be plus or minus 1. So let's go ahead and do minus 1 first because it looks a little bit more like that one. Is going to be kind of like you have the first hyperboloid I drew up there, and then there's another one down here, kind of like that. Say this one has 2 sheets. And then there's this part in the middle where sort of if you tried to solve for z values in here, you would end up taking square roots of negative numbers. And so this middle region disappears. Oops, forgot my equal sign there. Sorry about that. And then if we have the exact same equation, but now it's just equal to plus 1, then we don't lose that middle region. And it's going to be like this, kind of. Imagine that those 2 bottom parts are about the same shape. And again, the pictures in the book are much better than what I do here. This is just kind of the very quick sketch of all those things. Gosh, we've already been going 10 minutes and I didn't want to spend much more time than this. So this section in particular, I'm going to say that you should experiment with GeoGebra or CalPlot 3D, as I linked to you in like class resources, to get a better intuition for these shapes. And we're going to get lots of practice with them in your web work, kind of distinguishing between them. Really, the thing to know is all these letters, A, B, C, help tune how wide and skewed the different shapes are. You know, when you're looking at this sphere, if we introduce more constants out front, we can introduce like ellipsoids instead of perfectly circular things. And oh wow, that's new. And just watch out for there being two parts of anything that has a squared component of the z above and below the axis. And these types of shapes are things that we'll work with a lot when we learn to integrate over them.